You had to rent a car to drive home, all that good stuff. Then the rental car company wanted to give me attitude. That wasn't happening. So I know what you mean with insurance companies suck, Ashley. Yeah. Mm-hmm. Ah. Oh, well, that's fun.
Yeah. Mine has been good.
Yeah.
Yeah,
That sounds right. How goes it? After that fun little story.
I wish it wasn't as windy outside.
Oh, is it windy? No.
Yeah.
It's like really nice, but it's like I wish the wind would turn back a little bit.
Yeah.
This is not ideal disc golfing weather.
No, it's really not ideal disc golfing weather.
I went disc golfing one time, and my brother got poison ivy because I threw it in.
I lived in Huntington, West Virginia for a couple of years, working at Marshall University right out of grad school, and there was a disc golf course, and I was living by myself at the point, so I was looking for things to do. So I played the first 3 holes and couldn't find the 4th. Well, I guess I'm done. Now, apparently you had to basically bushwhack through this part of this park to get to the next hole. I'm like, well, how about a sign at the very least saying, go through this brush? I mean, it was ridiculous.
Yeah. So now a little bit more refined.
Yeah, this one was not. Well, of course, it was fit right in line with not being overrefined in West Virginia, but that's another story. Any questions on anything before we get going? The scenery was beautiful. It's a beautiful state.
Oh yeah, and you said like it's like shitty otherwise.
Yeah, pretty much. Yeah. Yeah.
I get car sick every time I go.
My car insurance there was probably twice as high as it is here, and that was older cars because of all the uninsured motorists there.
Oh.
Sure.
Oh.
Yeah.
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 Is it illegal not to have insurance?
That doesn't matter. Apparently. Yeah, it's state to state, but yeah, I don't remember what was illegal in West Virginia or not, but that didn't really matter. Yeah, so lots of things about West Virginia I didn't care for. The scenery was absolutely beautiful. Got some nice pictures, but did some winter hiking, saw frozen waterfalls, those kinds of things. That was cool, but
You ever go to Otter Creek Wilderness?
did not go there. But yeah, I mean, like I said, the scenery was beautiful, but that was about it. All right, so let's talk about some more hypothesis testing. How's that sound?
Yeah.
Yay! Anything said?
7.3.
Nope, this is going to be 7.4.
Nice.
Oh.
Hey, it's basically Friday for this class.
It is. And I'm not giving you homework for break.
This is technically my Thursday.
Today is not Friday.
Well, I mean, yeah, but like for this
All right. So let's see if we can do a specific example here and figure out what's going on, hopefully. So this is 7.4-1. We've got, we want to test whether the variance of a particular random variable is 525 squared versus, I don't know why they wrote it that way, but they did, versus the variance is actually less. I'm just telling you what the setup of the problem is. All right, so they have a distribution that they know is true. They've got the variances of birth weights of children in the United States. So they're telling you that the variance of birth weights of both boys and girls in the United States is 525 squared. And the random variable is comparing this variance to the variance of a baby girl born at home in Ottawa County. Well, I don't know where Ottawa County is, but since one of the professors was a professor at the University of Iowa, it could very well be in Iowa. But they're assuming that, they're checking to whether or not the variance of baby girls born in this particular county is smaller than the variance of all the children in the United States. Okay. So to be able to do this hypothesis testing, just like we did for proportions, just like we did for means, just like we did for differences of means, we need to develop a test statistic in a critical region to be able to determine whether or not based on a sample, we think that we can reject the null hypothesis, right? Same idea. Now, of course, we're changing the population parameter that we're using. We did proportions back in section 7.1, but really we said that when we had our sample size was big enough, we used the normal approximation anyway, and did the normal z-score test statistic and used the normal distribution. Then we went to 7.2, did means. Instead, if it was large sample, we'll do normal. If it's small sample, we'll do t, and then calculate our test statistic that way. In 7.3, we did the differences of means, but again, we calculated our test statistic based on what the error was, the error part was, for essentially the confidence interval, that standard deviation piece that either had the pooled variance or it didn't, depending on whether or not you assume the variances were equal, right? But again, then we went to the normal distribution table or the t-distribution table, or used Excel, based on if it was large or small sample, right? So everything so far has either been a normal distribution or a t-distribution, based on what the parameters are. Is the same distribution going to work for variances? That was a really long-winded premise to get to this point, but is the same distribution going to work for variances? No. What do we have to use for variances instead? Chi-squared, right? So we know that our if we do n minus 1 s squared over sigma squared is chi-squared of n minus 1, right? We agree? Okay. So when we're setting up a critical region, this idea here is going to have a chi-squared distribution, which again looks something like, well, not quite that drastic on the tail, but I'll call it good. Looks something like that, right? It starts at 0 and goes on forever. When we base our critical regions on this particular distribution, it will depend on whether or not we've got a left tail. The left tail here, of course, stops at 0. Whether or not we've got a left tail, a right tail, or a two tail. It's the same idea we do with normal distributions. If it's one tail, we'll pool all of the probability in that one tail. If it's two tail, we'll split it in half, just like we have, right? Same idea. In this case, it's a one-tailed test. It's less than the 525 squared. So we need to figure out a chi-square value here, where this is 0.05. I think they said use alpha is equal to 0.05 here, or in general, just your alpha. And then our notation for this, again, remember, is 1 minus alpha. It's the complement. The alpha part usually refers to the top tail, so they use the subscript of the bottom tail. So that's always the 1 minus. And then we would have n minus 1 here, whatever that happened to be. So we want to know if our test statistic ends up down in this region, right? We agree? So how do we get to that test statistic? Well, we know that this piece here is chi-squared of n minus 1. So if we think about just setting an equation, we had n minus 1 s squared over sigma squared is equal to this chi-squared value. This would be the value of the, if we think about it this way, if we did the sample and we put in the sample variance here and calculated this, this would be hitting right at the boundary, right? Anything? Okay. So our s squared part here, we would want this to be whatever that happens to be. So this critical number, we're trying to find the critical number again, essentially. If we solve this for our s squared, we would have sigma squared chi-squared of 1 minus alpha of n minus 1 over n minus 1. Right? Just rearranging that. So this is our critical value that we're going to use to determine whether or not we're going to reject. So in this is for a left-tailed test. But for a right-tailed test, of course, we would just use x, the chi-squared of alpha. It would be on the right side. So the only thing we have to determine is whether or not we're looking to see if our variance is less or variance is greater. In this case, since we're doing the left-tailed test, we want to check if this is less than this value or greater than. For this particular test, we want this one to be less or greater, given the test that we're using. Will be less, right? Because we're trying to see if it's less than, correct? Since we're doing the left-tailed test. All right. So when we do this, then, I mean, we rearrange this. This is the way the book has it written, but we could have also just done the same thing here, right? We could have just computed this value and checked whether it was less than this critical value, just like we did with the z-scores, right? This computation here is kind of like you're doing a standardizing of the distribution, like we do with the standard normal when we do the z-scores, right? We're basically standardizing it so it's a chi-squared. So you can actually do this and then call this your test statistic and compare it to this critical value, if you think about it in the same context. The only reason why we did it this way is because this is the way they have it listed in the box on page 375 in the book.
And that's your test statistic?
Yeah, this would be your test statistic. This part that I've got circled would be the test statistic in this case. It's basically like what you do for your z-scores or your t-scores when you're standardizing the distribution. It's the same concept. They just have it written in the other way around for your critical region in the book. So anyway, if we do it with the same way that we did it in the previous, we would say that our n minus 1 s squared over sigma squared is the test statistic. And in this particular case, we would reject h naught if this test statistic is less than or equal to the chi-squared value. All they did in the book was rearrange the equation. This is more consistent than what we've already done with what I... Jeez. I should have stopped talking. Words are hard, yes. This is more consistent with what we have already done, right? We have done standardizing a distribution and comparing it to a critical value from a distribution table or from Excel. This is more consistent with that idea, isn't it? Okay. All right, so they also give you a sample in this problem. So let's see if we can do the hypothesis test here. So the sample they give you in the problem has 9 birth weights. 31, 19, 26, 57. I'm going to have to type these in anyway, but I'll write them down in case you want to write them down before I type them in. I can't count. That's 11 birth weights, isn't it? 36, 29. I just saw an odd number and assumed it was 9. It looked like it was a group of 9, but... I always find it interesting when they give the data in the book, it always seems like there's a couple that match. Like here, there's 2 that match. It always seems like there's 2 that match. I don't know why.
Make it easier.
They kind of think of it easier.
I have so many to choose from.
All right, so let's.
6, 2, 9. There's 3.
Oh, there's 3 of those? Oh, yeah, there are. Gosh. All right, so let's go over to Excel.
It's hard thinking of numbers.
It is hard thinking of numbers. There's not very many of them.
No.
Not at all.
0, 6, 2, 9.
This is a good one. Oh, let's do it again. All right, so we have. Stop it.
No.
Okay, don't stop it then. That's fine. 31, 19, 26, 57, 34, 59, 36, 29.
2, 2, 4, 6, 7, 2, 4.
You realize I'm reading them out of the book, right? That I'm pretty good at ignoring them. And I definitely don't need help making mistakes. I can do it enough on my own. All right. So this is our sample data. we're doing this for the sample variance, so we'll do the var.s of those. So there's our sample variance. To do our test statistic then, we'll do n minus 1, which is 10 for this particular one. We'll multiply it by the sample variance and divide it by the given variance, assuming the null hypothesis is true. Hi, Sam. All right, so the 10's representing our n minus 1. This is just what the sample variance was, and this is dividing out the assumed variance of the population. So that's our test statistic. See, I told you, I can make enough mistakes without any help, especially when I'm trying to type. All right, so we also need the critical value. So for the critical value, we need an x value that corresponds to a certain probability. So we need to use the chi-square inverse function. The first one will be your left tail, and the second one will be the right tail. This one doesn't have a two-tail, so you'll have to, if you need a two-tail, you'll have to divide your probability in half to find both of them. So to use this one, go down to our chi-square inverse. The probability was 0.05, and there are 10 degrees of freedom. This is our critical value. So you need to highlight that again, Megan. If you were looking for the right tail, you would just use the .rt and do the same probability. We'll do one like that here in a minute. You have to divide your probability by 2 because you'll want to divide your alpha into half again. Right. So you'll do 0.025 for the left tail and 0.025 for the right tail in that case. Yep. You can't just do the negative and the positive because this one's not symmetric about 0. We actually have to do 2 different commands to get it. Which is why there's not the two-tail option, right? Because it's not a symmetric thing. All right, so there's our critical value. We wanted to be less than in this case because we were a left-tailed test, right? So what's our conclusion then? We reject H naught. Yep, sure do. Right? Because the critical value here was less. Now, we can also get a p-value for this. So remember the p-value, again, is the probability associated with basically treating this sample as worst-case scenario. Right? If this were, you already have a sample that is this bad, and by bad I mean, assuming the null hypothesis is true, this is a bad sample, right? This would be the probability, this would be in the rejection region, or critical region. So this would be a bad sample if the null hypothesis is true. So what the p-value is, again, is the probability that another sample would be at least as bad if the null hypothesis is true. Okay? So for the p-value then, we can use the chi-squared distribution function. The x value that we'll use is the value of our test statistic. Oh wait, we would not reject here. I'm sorry, this is backward. The test statistic was greater than the critical value. Yeah, sorry. We do not reject here. My bad. I flip-flopped reading them. Sorry. We do not reject here. Do not reject. The test statistic is greater, and we're doing a left-tailed test. Why didn't you correct me?
Well, I wasn't confident. I was trying to figure it out.
I was pretty young.
Yeah, that's what it was. All right. My apologies. I just read the smaller. Usually, the reason I do that is usually I find the critical value first and then calculate the test statistic, and I did it in reverse. And my brain can't handle change.
I was like, before now, less than.
Yes, we reverse the natural order of the real numbers. So yeah, that's what we call less than now. Less than really means greater than. It's opposite day.
Opposite day.
All right. 10 degrees of freedom, and it's cumulative. So again, what we're calculating here is the probability that any other sample is at 4.1 for your test statistic or less. Now, before I hit enter, should this value, given the fact that we did not reject, should this value be less than 0.05 or greater than 0.05?
Great.
It should be greater, yeah, I agree.
Not by much.
Not by much, but it is greater. Yeah.
And you're comparing that to the alpha that they do?
Yes. Yeah, because it's another way that you can actually do whether or not you reject. You can calculate the p-value, and if the p-value is greater, you don't reject. If the p-value is less, you do reject. You want small p-values. You want the probability that this was a bad sample to be small. So you want small p-values. Yeah, okay. All right, so this is relatively small, just not small enough. Yeah, Alex.
So the value we got for S squared
Mhm.
by doing it here on Excel is different than if you were calculating for S squared and then plugged it into that.
Say that again.
So the value we calculated for variance is right by just having Excel and using the data we have.
Yes.
That's different than if we would have solved the test statistic for S squared like we did earlier. So
That's why I did this here.
yeah. Why those two values different? Like the S squared, we just
Well, the S squared itself isn't quite a chi-square distribution. We have to multiply it by the number of the n minus 1 and divide it by a sigma squared to get a chi-squared. That's why I have to do this adjustment to compare it to the critical value. Or if you do it the way the book wrote it, you could have taken the critical value, multiplied it by sigma squared, which was 525 squared, and divided it by 10. And then compared these two values.
yeah, that's what I was wondering why those two were.
Well, why the two aren't the same.
Yeah, no, you get that.
Oh, okay. I did it the other way as opposed to the way that we looked at it because I think it's more natural to what we've been doing,
Okay.
right? Because the way we've been doing it is we specifically went to either the the standard normal distribution or the p-distribution to get a critical value and didn't adjust that value, right? We literally got the critical value. We did the adjustment when we calculated the test statistic. And now in the book they flipped it,
Yeah.
right?
Yeah.
Yeah.
So then would you compare that number to the variance they gave us?
Yeah. Yes. You would no. You calculate. You use the variance they gave you to calculate this number
Right.
and compare it to the you still compare it to your sample variance. Yeah. And you come to the same conclusion. It still doesn't last.
Yeah.
I don't know why they flipped it around on you because what we did here is the exact same process that we did before, right? We looked up a specific number that came from a standard distribution that we're used to, and then calculated a test statistic to fit it to that distribution and compared the value. Right? That's what we've been doing, which is why I'm going to do it that way. But the book in that table wrote it a different way. Which I thought was weird, but I wanted to mention that's what it was doing and why we weren't going to do it that way. Well, I'm not going to do it that way. If you're okay with that. And if you're not, tough. That's the way I'm going to do it anyway. All right. This okay? All right. So let's do one where we go the other way. This is 7.4-3. I wish there were just more board space in here. So I just would write it on the board instead. I'll flip back over. All right, so 7.4-3. We have our null hypothesis is that the variance is 140 squared, and the alternative hypothesis is that it's actually greater. Do you want to know what the context of the problem is?
No.
Yes? Let X equal the number of pounds of butter fat produced by a Holstein cow during the 305-day milking period following the birth of the calf.
That's exactly what I wanted.
It's exactly what you suspected, isn't it?
So at 305 days, you have like 2 months off.
Yes, yeah.
That's kind of like a teacher.
They got like 8 years.
And they certainly have got that down to a science to where we're only going to milk for 305 days. Yeah, that's weird. All right.
It's come a long way.
So what's that?
It's a bummer, come a long way.
Yeah, it has. All right, so we're going to use alpha's 0.05. We're going to have 25 observations. We'll do that. I'll type those in a minute. I'm going to write them all down. All right, so in this case, we're doing a right-tailed test. So when we find our critical value over here, this needs to be 0.05 on the right tail. So this will be your chi-squared of 0.05 on 24 degrees of freedom here. How do we know what? I'm sorry. Because it's greater.
Oh, that's right.
Yeah. That's how I know it's right. Yeah. I have no idea why we're doing it, but that's okay. I'm sure there's
The
some.
stats book said so.
I'm sure there is some agricultural expert that needs to know the variance of the butter fat produced by a Holstein cow. All right, so let's type these in. Let me zoom in a little bit so you can actually see. 425. One of these days, I'll just have somebody enter all this data out of the book into Excel, and I don't have to worry about doing it every time. Could have Haley do it.
Or you could be like Dr. Lee. Dr. Lee puts it like, has everything saved on a G drive.
Yeah.
Yeah, I know. Doesn't been saved for a long time.
You know, I mean, you're just learning the techniques, right? It really doesn't really matter what the data is.
No.
Data are.
Data was.
Data were.
Data was.
Twas.
Yeah, was.
There we go. There I got 25. A lot of numbers.
You're a lot of numbers.
You're a lot of numbers. All right, let's do the critical value first this time so that I don't screw this up like I did last time. All right, for the critical value that we need this time, it's a right-tailed test. I need the chi-squared value associated with the right-tailed test, so I'll use the chi-squared.inv.rt. I'll do this in a second. I was going to say I don't have all the data on here because the 25 is cut off. If anybody's actually typing it in, I saw you were typing it in. The last number is 975. Yep. All right, so then the probability was 0.05, and there are 24 degrees of freedom. Notice I don't use 0.95 here because it actually is calculating the probability from coming from the right to the value. Since it's got the RT. If you use the regular old chi-square inverse and not the right tail, then you would use 0.95 here. All right, so there's our chi-squared value. This is our critical value. So are we looking to be bigger? Do we want our test statistic to be bigger than that value or smaller than that value? Bigger. All right. When we calculate our test statistic, then what do we do? It's find the sample variance. I'll do this off to the side here. So sample variance of A1 to A25. All right, so then what do we do to calculate our test statistic? N minus 1, which is 24 in this case. Good. Yep. By the variance that's purported by the null hypothesis, correct? Okay. And again, we want this to be greater. Oops, it's not, is it? Okay. You want me to highlight the formula again? What if I say no?
That was really awkward at that point.
Well, Ashley needs the formula, so you have to hang up with Ashley.
It's 29.2 something. Well, it's 17. 17. 17.
176. 5.
177. Mine doesn't.
Oh, Ashley, you goofed.
That's not the same number. You do. Did I grab the wrong one? I got the wrong one.
Did you do the sample variance?
Or did I type it up?
Okay, there might be a number that you have wrong. Maybe it's not typed in right.
What was the last number?
975. Well, anyway.
That's the worst part, is typing in.
It is the worst part of typing in the numbers. I agree. That's why I had them typed in for you for the last test. Yeah. So, do we reject or no?
No.
No, because we need to be greater than. Did you find it?
Yeah.
What would be our conclusion?
Do not reject.
I meant for the problem.
Oh, for the problem? There is not sufficient evidence to indicate that the amount of butter fat, the variance in the amount of butter fat produced by Holstein cows in the 305-day milking period after the birthing of a cow is greater than 140 squared.
Dr. Lee would love that.
I know she would.
Dr. Lee
That's what you should be doing if you're interpreting the statements. I'm just not worried about the interpretation.
So like in the T and the normal ones that we did, we had like Z is greater than a critical value.
Mm-hmm.
What, like, do we use like the chi-square?
I would use a chi-squared if you're going to call it something, yeah. Reject if chi-squared is greater than that. Yes. Oh, okay. Guess she forgot to do it Monday. Yeah.
Yeah.
I should have taken a video.
Yeah.
I thought she was going to be here. She said she was leaving like shortly before.
Yeah, well, she told me yesterday that the coaches changed the time that they wanted them on the bus. So, yeah. So, neither was she. So shockingly enough, yeah.
Will we have to use a Taylor's distribution at all?
Not for these. No, these are all chi-squared.
These are all chi-square?
Yep, these are all chi-squared.
Everything's chi-squared.
Well, except for when we do ratios of variances, then what it'll be.
Well, this is chi-squared.
That'll be the F distribution, right? So, all right. So, let's see. Is there one in here with an F1 that I want to do right now? This
I
is,
just want to end right now.
what'd you say? You want me to end too?
Yeah, you just want to end right now.
Okay, fine.